I spent decades staring at equations that described something so strange, so impossible, that even I struggled to believe what the mathematics was telling me. Black holes, places where gravity becomes so violent, so absolute, that it tears apart the very fabric of what we think we know about reality. And yet, for most of my career, I realized everyone, including most physicists, was getting them fundamentally wrong. Not wrong about their existence, wrong about what they actually are. People think black holes are cosmic vacuum cleaners, sucking up everything around them. They think of them as holes punched through space, or as infinitely dense points of matter crushing down forever. Some imagine them as tunnels to other universes, or as cosmic drains where things just disappear. No, that's not what they are. A black hole is something far stranger and far more precise. It's a region of space-time where gravity has become so intense that it creates an absolute boundary, not in space, but in what's physically possible. Let me show you what I mean. In 1967, when I was still walking, I sat in a lecture hall at Cambridge and listened to a mathematician describe something that shouldn't exist. He was talking about Schwarzschild's solution to Einstein's equations, a solution that predicted a point in space where, if you compressed enough mass into a small enough volume, you'd create a surface from which nothing, not even light, could escape. I remember thinking, that can't be right. There must be some mechanism, some process that prevents total collapse. There isn't. Here's what actually happens when a massive star dies. The fusion reactions in its core finally stop, and without that outward pressure pushing against gravity's inward crush, the star collapses. If it's massive enough, roughly 3 times the mass of our Sun or more, nothing can stop that collapse. Not atomic forces, not nuclear forces, nothing. The star crushes down past the point where atoms can exist, past the point where even atomic nuclei can maintain their structure, down to densities that make neutron stars look spacious. And at a critical radius, the Schwarzschild radius, something extraordinary happens. Space-time itself becomes so warped that all paths lead inward. Not most paths. All paths. From outside, you'd see the star's surface approaching this radius, but you'd never see it cross. Time dilation becomes so extreme near the boundary that, from your perspective, the collapse appears to freeze. Light from the star shifts redder and redder, dimmer and dimmer, until it fades into darkness. Not because the star disappeared, because the light can't escape. That boundary, we call it the event horizon. But here's where everyone gets confused. They imagine the event horizon as some kind of physical surface, like a membrane or a shell. It's not. There's nothing there. No material, no barrier, no substance at all. If you fell toward a supermassive black hole, 1 millions of times the mass of the Sun, you'd cross the event horizon without even noticing. You wouldn't hit anything. You wouldn't feel a surface. You'd just cross a line in space-time beyond which your future becomes geometrically required to move inward. Let me say that again, because it's crucial. Beyond the event horizon, moving inward isn't something that happens to you. It's the definition of your future. Just as right now you can't help but move forward in time, once you cross that boundary, you can't help but move toward the center. Not because something is pulling you, because the geometry of space-time itself has been so deformed that inward and future have become the same direction. I spent years trying to wrap my mind around that. What does it mean for space and time to exchange roles? Inside the event horizon, the radial direction, the distance to the center, becomes time-like. You're falling toward the center in the same way you're falling toward tomorrow. You can no more stop yourself from reaching the center than you can stop yourself from reaching next Tuesday. And what's at the center? The singularity. A point, or more accurately, a moment in time, where space-time curvature becomes infinite, where the equations break down completely, where everything we know about physics simply stops making sense. In the early 1970s, I became obsessed with a different question about black holes. Everyone was focused on what happens to matter falling in. I wanted to know what happens to information. Here's the problem. Quantum mechanics says information can never be truly destroyed. It can be scrambled, transformed, hidden, but not erased from the universe. But general relativity says anything that crosses the event horizon is gone forever, sealed off from the rest of the universe by an absolute boundary. Those two fundamental theories contradict each other. I remember sitting in my office at Cambridge in 1974, working through calculations about quantum fields near event horizons, and I found something I absolutely didn't expect. Something that contradicted everything I thought I knew about black holes. They're not black. When you account for quantum effects near the event horizon, black holes emit radiation, not from inside the horizon. Nothing can escape from there. But right at the boundary, quantum fluctuations in the vacuum create particle-antiparticle pairs. Usually these pairs annihilate immediately. But near the event horizon, sometimes one particle falls in while the other escapes. To an outside observer, it looks like the black hole is emitting particles, emitting radiation, glowing. The effect is incredibly tiny for stellar mass black holes. Their temperature is far below the cosmic microwave background. But for smaller black holes, it becomes significant. And here's the truly strange part. As a black hole emits this radiation, now called Hawking radiation, though I didn't name it, it loses mass. It evaporates. Given enough time, every black hole will evaporate completely. I published these calculations in 1974, and the response was skepticism mixed with fascination. If black holes evaporate, and if that radiation carries no information about what fell in, then information is destroyed. The universe itself would be fundamentally uncertain, fundamentally random, in a way that violated quantum mechanics' most basic principles. This became known as the black hole information paradox, and it haunted me for decades. People proposed wild solutions. Maybe information is preserved on the event horizon, encoded on its surface like a hologram. Maybe it leaks out through some subtle correlation in the Hawking radiation. Maybe black holes don't evaporate completely, leaving behind remnants that store all the information. I made a bet with Kip Thorne and John Preskill in 1997. I argued that information was destroyed, that we needed to accept this fundamental uncertainty. They argued it was preserved somehow. In 2004, I conceded, I was wrong. The mathematics, when worked through carefully with the full machinery of quantum field theory and curved spacetime, suggests that information is preserved. It's encoded in the radiation in ways that are fantastically complex and subtle, but it's there. The universe is strange, but it's not fundamentally random. Information survives even through the most extreme gravitational collapse we know of. But here's what still gets me, what I kept returning to throughout my career. We still don't understand what happens at the singularity. Our equations break down. General relativity predicts that space-time curvature becomes infinite, which is physics' way of saying, I don't know what happens here. We need a quantum theory of gravity to understand those final moments, the last microseconds before the singularity, where quantum effects become crucial and space-time itself becomes uncertain, fluctuating, probabilistic. String theory offers possibilities. Loop quantum gravity offers others. But we don't have definitive answers yet. The singularity remains hidden behind the event horizon, protected by what Roger Penrose called cosmic censorship, the hypothesis that singularities always form inside black holes, never naked and exposed to the outside universe. I spent years working on the cosmic censorship conjecture with Roger. We made another bet in 1991 about a particular configuration of rotating black holes. I argued that cosmic censorship would hold. Roger argued it might be violated under certain extreme conditions. I lost that bet, too. In 1997, computer simulations showed that certain configurations could, in principle, produce naked singularities. But here's what decades of thinking about black holes taught me. They're not exotic curiosities at the edge of physics. They're fundamental laboratories where our two great theories, general relativity and quantum mechanics, meet and clash. Understanding black holes means understanding how gravity behaves at the quantum level. And that means understanding the deepest nature of space, time, matter, and information. Black holes aren't just objects in the universe. They're windows into the universe's underlying structure. Every galaxy appears to have a supermassive black hole at its center, millions or billions of times the mass of the Sun. The one at the center of our Milky Way, Sagittarius, a star, has a mass of about 4 million suns, compressed into a region smaller than Mercury's orbit. We've now actually imaged the event horizons of supermassive black holes. First M87 star in 2019, then Sagittarius A star in 2022. Seeing that ring of light around the shadow cast by the event horizon felt like vindication of a century of theory. But it also reminded me how much we still don't understand. What's happening inside those horizons right now? What's the structure of space-time near the singularity? What happens to information during the collapse? How does quantum mechanics reconcile with the classical description of the event horizon? These questions kept me up at night. Well, many things kept me up at night. But these questions felt particularly urgent because they pointed toward a deeper understanding, toward a theory that could unify quantum mechanics and general relativity into a single coherent framework. I think black holes hold the key to that unification. They're extreme enough that quantum effects matter, but large enough that gravitational effects are classical and well understood far from the horizon. They're laboratories that nature has provided for testing ideas we can't test any other way. The fact that black holes evaporate through quantum processes tells us that quantum mechanics and gravity aren't separate magisteria. They influence each other. They're part of one consistent theory we haven't fully discovered yet. I made contributions toward that theory, so have thousands of other physicists, but the complete answer, the full quantum theory of gravity that describes what happens at the singularity, that resolves the information paradox completely, that tells us how space-time itself emerges from something more fundamental, that's still ahead of us. That's for the next generation to discover. What I can tell you, what decades of calculations and thought experiments taught me, is that black holes are real. They're precisely defined by mathematics that matches observation, and they're far stranger than the popular imagination suggests. They're not holes. They're not vacuum cleaners. They're not tunnels. They're regions of space-time where gravity has warped geometry so severely that escape becomes geometrically impossible, where time and space trade roles, where the future points inward, where quantum mechanics and general relativity dance together in ways we're still learning to understand. And they're everywhere. Stellar mass black holes by the millions in every galaxy, supermassive black holes at galactic centers, possibly primordial black holes formed in the early universe, perhaps even microscopic black holes forming and evaporating in high-energy particle collisions. When you look up at the night sky, some of those points of light are galaxies powered by supermassive black holes at their centers. You're seeing the glow of matter spiraling into the event horizon, heating to millions of degrees before taking its final plunge into a region from which no signal can ever return to tell us what happened next. That boundary, that absolute limit encoded in the geometry of space-time, fascinated me my entire career. Not because I wanted to cross it, but because understanding why it exists, how it behaves, what it means for information and quantum mechanics and the nature of time itself, that understanding teaches us something profound about reality. The universe has rules. Deep rules, mathematical rules, rules that don't care about human intuition or preference. Black holes are what happens when matter and energy concentrate so intensely that those rules create something that looks impossible, but is, in fact, inevitable. I spent my career exploring those rules, pushing against them, testing their limits, looking for exceptions. I found very few exceptions. Mostly I found that the rules are more subtle, more beautiful, and more unbreakable than I initially thought. Black holes embody that lesson. They're not violations of physics. They're physics operating at its most extreme, most unforgiving, most fundamental level. And we're only beginning to understand them.